Thank you, sir. Okay, we're still working with buffers, except what we're going to do is we're going to have a couple calculations. Well, I guess we could just show you. I think I wrote it down here, did I? Yeah. We're going to encounter two problems. We're going to have a buffer, and we're going to add some strong acid or some strong base and ask what the new pH is. If we add some acid, strong acid, Jamesa, what's going to happen in that buffer to keep the pH relatively the same? Jamesa, what's going to happen in that?
Well, if there's a buffer, then shouldn't it not really change?
Shouldn't really change, but what would really happen?
It would change a little bit.
What's going to have to? Something has to react with this strong acid. What? The conjugate base, right? So we should probably write down that little expression. Might help you see what's heading our way here. pH equals pKa. And let's write the form I like. Moles conjugate base, moles conjugate acid. Okay. So let's say we add some strong acid, just to give you the big picture of what's going to happen here. And Jamesa said the conjugate base reacts with it. So if the conjugate base reacts with it, this number is going to go up or down? It's going to go down, right? Because it's reactant. That number's going to go down. Is anything going to happen to this number? It has to, right? Because the conjugate base gets converted to the conjugate acid. So it has to go up. Okay? But remember, it's a weak system, so the pH isn't going to adjust too much. But if you add an acid, you bet the pH is going to drop a little tiny bit, but not a lot if that buffer wasn't there. If that buffer wasn't there, it would have dropped like a rock. But with the buffer being there, it's relatively the same. Okay? And then those are the numbers we're going to be playing around with. So we just have to keep track of what's reacting, what's being produced. Or another type of question, how much of a strong acid or base is needed to get the pH to a certain value. So we want to get the pH over here. How much should we add? Again, we're playing around with these numbers and keeping track of them. Well, to me, that means ice, mole table. Okay, we've done this a lot. And Henderson Hasselbalch way of writing that ice table is really nice because it has the pH in it. Everything's all nice and ready to go. Okay, so let's just keep using it. So that's kind of the big game plan. Let's see how it works here. Just jump right into it. Okay. How many mils of 0.289 molar HNO3 or 0.320 molar NaOH, not saying which one, should be added to 128 mils of 0.0078 molar ethylamine to give a pH of 10.78? I don't know. See, that's what I'm kind of thinking too. At first glance, I was kind of thinking, that's really basic. So that means we're probably adding NaOH, right, to make some base. But what if it would have been 7.6, 6.3? You can't really go by that. What you have to go by is, what do you have here? Remember that big M means that's the exact form that you have. They have a bottle of ethylamine. So this is what you're starting out with. It would be a lot easier if we had the photographic memory and you're looking at that ethylamine table and, ooh, I know exactly, it's the acid form, or ooh, it's the base form. I don't have a clue. So I have to look at the table. And I don't have a table. Yeah, we said it was AP 11 or something. Good, very good practice. If you've got it, you should whip it out here. AP 11. It's not the easiest thing to find. Okay. All right. Since the poor handicapped lady didn't bring it. But the cost of borrowing my book is to tell me, is ethylamine, is that the, I guess we could say, is that the HA or is it the, which one is it?
It's a conjugate base. Because I said I didn't really understand this yesterday. This has an H plus.
It has an H plus.
So then we need to make it.
You have to make it neutral. Neutral is always the name.
Okay.
The name is always neutral. The guy in the table is not neutral. You got to make him neutral.
So we need to add conjugate base.
So that means you got to rip off an H plus. That means the form you have is the base. Right. Seems like everybody agrees on that. I just heard a lot of base. So we have ethylamine. We have the base. We have the base form. So, was our initial guess correct?
Yes.
Wait, no. Whoa. Because we have to add acid then.
We have to make it.
Right? It's a base. It's a base. So you have to assume that they selected a buffer that's appropriate, right? So if they have all base form, it's way above your design. Sorry. Yeah, the pH is way above, right? The pH is way above where you need it. Because we're assuming that they're picking. How are you supposed to pick these buffers in the first place?
The one that PK is closest to the pH that you want.
Closest to the pKa. That pKa is really close to the pH. So that pKa should be really close to 10.78. If it's not, this whole game of adjusting isn't going to work very well.
It is.
Okay. Oh, it is. Nice. It's 10.6, so that's why it was selected. So if you have all ethylamine, it's all base form, it's a lot higher than 10.78, because 10.78 is where the populations are or not 10.78, what is it in there? pKa is
10.673.
10.673. At 10.673 pH, what are the populations of the conjugate acid to the conjugate base? They're equal. They're exactly the balance. They're exactly the same. Right? Because you're right in the middle of the buffer region then. You can add acid, you can add base, you're right in the middle. So if we're going to start out with 128 mils of this ethylamine, you have all base form. We have to adjust the pH to get to 10.78. Sounds odd. I still think it sounds odd because 10.78 just sounds so dang basic, and I don't know, how can you just imagine it being, oh, you're at 12, you're at 14 or something. Right? You're way too basic. And the other, but to me, I think it's easier to think of it this way. You find out what that buffer is. It's a base. The only thing you can add to it is a acid. You add more base, you're out of the buffer region. It's all base. You're out of the buffer region. It's no good. It's not a buffer. So if your form of your buffer is conjugate base, you can only add an acid. Okay. So, if we can only add an acid, because remember we said the goal here, what I'm doing, I want to make a mole table. Ice, same thing. Okay. But the book calls it mole table, so that's what I'm going to call it. Okay. So do you see why I put A minus plus H plus? Because that's what has to be happening. All I have is A minus. A minus has to be on the reactant side. Because you identified ethylamine as A minus, the conjugate base. So you're comfortable with A minus being on the reactant side. That's where it has to be. And it has to react with H plus. What's this H plus? That's coming from where? The nitric acid. It's coming from right here. We're not adding that stuff. That ain't going to work. All right? We're adding that it's that nitric acid. Okay. So let's pick on urandi. What is it going to form? It's just going to form HA. That's it. Now it might have been easier. It might have been easier for your Randy if we would have actually wrote out the structure for ethylamine, and then you'd see, oh, okay, it's going to form what's in that bloody table, right? But I don't know. This seems it's the same thing. You get the same answers. Why not just write A- for ethylamine and HA for its acid form? That's how it. If you prefer to write ethylamine, go ahead and write it. I don't even know what it is. You'd have to look in the book and see what the formula is, right? CH3, CH2, and NH3 plus. Well, NH3 plus would be the HA side. The NH2 would be the ethylamine. Okay. So does that make sense so far? Pablo, did I lose you? You good? Okay, he's good. So let's keep going. Nyla, we got to fill out that initial row. What are we going to put in there? Moles of the ethylamine and put that under the A-. Okay, how do you get moles? Yeah. So we're going to do what right here? Take 0.0078 big M times, which is really moles per liter if you want to show everything, times 0.128 liters. Just moving the decimal place over, right? So all that is under my A-. That's my initial. It's just the moles, right? You could have done that off to the side, but you just get the volume times the concentration. And let's spread this out a little bit. Do I have any H plus there initially?
No.
We're going to add that later. That's our change, right? So nothing. Do we have any conjugate acid present initially? No. Okay. So we just have that ethylamine. Remember the ethylamine with the big M? You only have that form. That's it. So the change. Okay. Jeff, what do you think we should put in the change row? Yeah, under the A.
It's only one small to one, so it's
Just
your answer is minus X, right?
yeah, negative X. Yeah, he's right. If there's a 2, it would be negative 2X. Under the H, everybody? Yeah, that's kind of odd, isn't it? It's not there in the first place, but technically,
Okay, it's still minus.
all right. But we're gonna see it doesn't really matter. We're gonna this if it bothers you, just who cares? Whatever you write there, it doesn't matter. Okay, the HA would be positive X, right? Because we're forming that one. Now, what was that? What's the molarity times that constant times the volume? What did you get as a number? 9.984 times 10 to the negative 4 minus X. Minus X, even though that kind of looks weird, doesn't it? Okay, X. So what are we supposed to plug it into? Well, our Henderson Hasselbalch equation. pH equals pKa plus the log moles of the base form all over the acid form. Okay, and remember, here are all of the answers. Those are all the concentrations at equilibrium. And it looks really weird, this guy, right? Doesn't it? But he doesn't go in here. He doesn't go in here. Right? So that's, even though this guy, he really bothers me. I don't know. There's nothing there. How can you have minus X? You know what I'm saying? It's because he's added externally. That's where he's coming from. He's the amount of HNO3 that we added, the moles of it. That's what X is. So it really doesn't fit in. But the pH, everybody has to be 10.78. See, we're getting somewhere here. 10.78. And someone, Jamaica, you told me, I forgot already. What's the pKa for that thing? 10.673. So that's the pKa for my ethylamine buffer. plus the log. Now the moles of A minus, we put 9.984 times 10 to the negative 4 minus x. Minus x. And then the denominator, we put x. Solve for our x. Solve for our x. Can we drop that negative x? Don't do it. It's not helping you at all. You're not saving yourself from a quadratic. It doesn't, I mean, it doesn't, no. This is a really dinky number. 0.00. Come on, no, don't drop it. Don't drop any x's in mole tables because you want to keep track of every single mole. Because this really technically isn't an ice table because that negative x doesn't make, it's the amount you added. So you don't want to be dropping it. It's the amount you added. Okay. So we got to solve it. So what would you do first, Miriam, to solve this thing? Not dropping anything. Oh, hold on though. He's all inside the log. I don't think you can mess with him. There. Okay, now you're seeing it. You see that? We got it. In the end, we have to raise both sides to the 10 power. So prep it for that. Bring that 10.673 over here. So prep it for that. Let's see. So we'd have to take 10.78 minus 10.673, about 0.107. So that is the log. Now you raise both sides to the 10 power, right? So we'll have 10 to the 0.107 equals, the other side would just look like what? Yeah, just what's in the parentheses, right? Because the log disappears. So do you see how things really would have messed up if you would have dropped that x? You can't do it. It doesn't. You're not gaining anything anyway. Okay. So you're gonna have to probably do what? Let's see if someone has an idea here. Erica, how are you gonna solve this? We gotta solve for x. Oh, well, what do you think?
Can't you? Right, I'm not good with math.
That's why we're doing it.
What I would do, and I probably would be wrong, is that I would drag the x that's on the denominator to
Yeah.
the other side.
Oh, good. Bring that up here. You hear what she's saying? Okay, that's an excellent first step. That's what I would do too. Okay, then what would you do? You're on a roll.
Well, since that's minus x, wouldn't you minus the 9.984 times that? So then you get the x by itself on that side, and then you divide
There you lost me. She brought the x up here. And then maybe she said this. Combine the x's. Combine all the x's, right? So bring the x up here. See what that number is going to be? 10 to the 0.107 times x. See what that number is going to be? Combine it with the negative x. So you end up with a number times x. You can solve for x.
Yeah, way harder than it needs to be.
Well, how would you do it? What's 10 to the 0.107?
Bringing it over to that.
1.287.
4.279.
Okay.
Right. X.
Yeah, just bring the x over here, right?
Right. Okay. That's
Oh,
what you-
okay.
I thought you said like bring it up to the x part, and I was like, what are y'all doing? Okay.
I get it.
Right? So combine the x's, combine this with this, then you can solve for your x. It's not a quadratic. It's just add x to both sides, right? See if you can get an x. See if you can get an x out of that.
I got 3.9 times 10 negative 4, but I don't know if that's right.
That's not what I got. I could have done it wrong. What did?
I got 4.3.
Yeah, 4.38 times 10 to the negative 4.
Yes, I got.
Okay, a bunch of people are getting that. 4.38 times 10 to the negative 4. Make sure you can get that. Okay. So once you get it, go back to the problem and see if that's your answer or what.
Yeah, okay. I see what I did. I typed it wrong.
So anyone having trouble getting the x? All right. So add x to both sides. So you'd have 2.27938 equals that number. Then divide both sides by 2.27938. So you divide this by 2.29738.
Right side over here, so instead of 227, it's 2.
Yeah. Okay. So John, you got that?
Yep.
All right. So is that my answer or what?
No, because I'm counting pounds.
Put that where.
All right. Give the guy a chance here. How are we going to get our answer then? Final answer. What are you going to do? What does the x represent? All right. Now I'm not. It doesn't help much to look here. It doesn't really even help much to look here. But right here, John, that x represents what? How much we added. But what are the units? Moles. Yeah, not moles per liter. Moles. We got rid of the moles per liter, right? We converted everything to moles. So this is a mole table. So we could have made a concentration table, but I don't think it would work too well. So we have a mole table. I think it might have worked with concentration. Anyway, those are the moles. No, we need to make a mole table. You can't make a concentration table. So those are the moles of H+. So how does that help you? Anybody see it?
So you get the moles of the H and the result that you get from
The moles that we got, 4.38 times 10 negative 4. And that's the moles of H+. And use the molarity of the HNO3. In fact, we could write it as what over what? Times, yeah, flip it. Put the liters on top. In a liter, we have 0.289 moles of H+. I don't need to write the HNO3 because it's a strong acid. So it'll look better if you don't write the NO3 part. It's easier to see. So our moles will cancel. We'll end up in liters. Oh, and they wanted milliliters. So in a liter, 1,000 mils. And then we'll have our answer. 1.15 milliliters?
2.
Oh, 1 point. We can't measure that much volume anyway, right? So we're like 1.5. Okay, so you had about 1.5 mils of HNO3, and that'll get you there. It's kind of nice because otherwise you're just randomly dumping in HNO3 or NaOH, right? To actually have a rough idea of what to do. It's pretty helpful. So what did we do? First we just, whether they're adding, clean this up a little bit, you have to figure out to add acid or base. And because they give you those choices, so you have to look and see what the buffer is. See what form it's in. You have to use the table to do it, starting on AP 11, right? Is it the conjugate acid or conjugate base? Once you identify it, if it's the conjugate base, like this case, you can only add HNO3. If it would have been the conjugate acid, you'd have had NaOH. Okay. Well, the table, no, remember the table, sometimes you're going to end up with a conjugate acid in the table. Sometimes you're going to end up with a conjugate base in the table. Well, it's not really, the table doesn't matter. What matters is the name, the form that's neutral. You're going to rephrase what you said, Pablo, it's going to be the opposite. You're going to add the opposite of whatever form the buffer's in. That's how you'd want to say it. And the form the buffer's in is always corresponds to the, which form? The neutral, right? The neutral form. Okay, and just have to look at, and that's when the table comes in to tell you whether it's an acid or a base. Unless you want to memorize all that stuff. Okay, then we set up a mole table, and it just goes from there. Use the Henderson Hasselbalch equation. Okay, so any questions on the big game plan? Right, the chemical reactions whose equilibrium constants are Kb and Ka for imidazole and imidazole hydrochloride, respectively. So let's just some practice here. Imidazole. What the heck is this stuff? So it wants us to write Kb and Ka for imidazole. Okay. Did you find it? So in the chart, is it neutral? Nope. It's not neutral, so you got to remove an H+, so that means imidazole must be the conjugate base, because you had to remove an H+ to get there. And they're kind of hinting at that, you notice? Kb and Ka for imidazole and imidazole hydrochloride, respectively. All right. What's the hydrochloride thing doing in there? Yeah, it's not even in there. Yeah. Yeah, you're close. I think you got it. Because if you're going to grab a bottle of something, it has to be neutral, right? It'd be really nice to grab a bottle, and for some reason, who knows why, they don't want the conjugate base form. They want the conjugate acid form. So because we just want to add base to this, right? They want a bottle of the conjugate acid form. But the darn thing has a charge. Right? Look at the table. Imidazole, the acid form has a charge. You can't have a bottle of something that has a charge. So you make it, if it has a plus, just attach a what onto it? And starts with an A, and anion. An anion that has no acid or base properties. Look at that chloride. Dang, he's perfect. Right? The conjugate base of a strong acid, he's not going to do anything. There's no pH properties at all involved with him. So attach a an anion, specifically a chloride anion, to any of these guys with a charge, and you can start out with the acid form. So I guess that means when we're doing these questions, we kind of got to be a little careful, right? If they say a hydrochloride, that means, oh, we're messing with the acid form because they have a Cl minus on there. Whatever it's attached to is what it has a plus. That's going to be the acid form. So you got to kind of be careful. Okay, so let's write the Ka and Kb reactions for these guys. And if you don't have a book, we need to write down what... Yep.
It has 2 Kas.
Okay. Yeah, because there's 2 acidic hydrogens. And we're only messing with the first one. See how there's 2... Nyla pointed out something, and we're going to talk about that. It's coming up. And these... in a lot of these compounds, there's more than one blue H. So that means there's more than one acidic hydrogen. So there's more than one Ka then. Okay. But that doesn't hurt anything. Just kind of disregard that second one. It's that first one we're interested in. It's going to take a lot to kick off that second one usually. Yeah.
At least for now.
Yeah. Well, you could. Where's the Midazolam? See, actually, it kind of. Think of it as a selling point. You want to sell this somehow you have a Midazole factory, right? And it looks like, if you look at your chart here, 6.993. Dang, that's so close to pH 7, neutral, it's good for this, it's good for the drug designers and all this stuff. And then you can go on and say, now, I know it's rare, you hardly ever use it, but I can also buffer pH what? 14.5. You're hardly ever going to use it, but, it might be a selling point. But you're never going to, it's so rare, right? So it's that first one. So you pretty much you disregard it. Okay. So go ahead and write the Ka and the Kb reactions here. I wanted to write down what it was. If you look in the table, I'm not very good at doing this sort of thing. Not if they ask this, though, right? No, for the test, dang, I would be writing HAs and A minuses for these mole tables. But if they say write a Ka reaction, yeah, good luck with that. You're gonna have to draw this thing out. There's a double bond there. Since I have the plus written on there, that must be the acid form. So then, right? Just write the Ka reaction. So this would be the hydrochloride. So I should technically write a. Right? Because they want it for the hydrochloride, so I should probably show. Oh, okay, that's how he's a neutral compound. Okay, they call it the hydrochloride. So it's Ha goes to A minus plus H plus. Then I'm tagging on this chloride just to balance things. Now I got to draw the A minus dude. That H is gone, right? There, something like that. So this is what we're calling our A minus, and this is what we're calling our HA. And that's the Ka reaction. Then you got to do the Kb reaction. So that would be this guy plus H2O makes this guy and OH minus, and you wouldn't have any chloride in there. Well, you could, but then you'd have to add it over here too somewhere. Looks kind of weird, but the reason why it's in the Ka reaction is because they said specifically write the Ka reaction for imidazole hydrochloride. So if you want to write a Kb for imidazole, they didn't say anything about the hydrochloride being the acid form, so it's kind of left it alone. A few minutes here. Calculate the pH of a solution prepared by mixing 1 gram of imidazole with 1 gram of imidazole hydrochloride and diluting to 100 mils. Wow. Is this a buffer problem? Is this guy a buffer? Then it's a buffer problem. All right. So write the buffer equation. The dude. Well, the two dudes. There's two of them in there, right? Okay. Does it look like the 100 mils is going to matter? No, I mean it would have if we would have wrote the equation in the form of concentrations, but the volumes cancel anyway. So we just need to look up the pKa of the stuff, and you need to put in the moles of the conjugate base, the moles of the conjugate acid. The trick to it, I think, is getting the molar mass. How do you get the molar mass of this guy? What's that? Yeah, periodic table, but the structure's in here, right? And the structure in here never, ever has the chloride. So you have to realize he's there. So you have to, if I was a imidazole, we kind of wrote him down already, right? Let's find let's to make sure everyone's on the same track here. Find the molar mass of imidazole hydrochloride, right? It'd have to be this guy. So in the table, it doesn't have the Cl minus. You have to add that in. If you don't add it, you're going to be way off. All right? So we're about out of time, but we have a couple minutes. So you have time to get your exam then. So